All right. Okay. So yeah, a couple minutes late, but well, none the worse for wear. We got 3 hours. So today is July 23rd, and we are here in the calendar. So you should have finished lab 4. Assignment 4 is due this weekend. I think I made it accidentally an easy assignment. It's not to say that you should wait to get started, because conceptually easy and implementing it are two different things. So, I mean, do get started, but I think, for anybody who's trying to make up marks, definitely devote a couple days to this and you can probably get full marks without too much trouble. Assignment 5 should be ready to go next week, hopefully. I'm coordinating with a TA on that one. It will be on graphs, which we will take next week. And I mean, there's an opportunity there, I think, to do something a little more interesting, because although it is a graph problem, the graph implementation in the ODS library is not really sufficient for this problem, or rather, it could be improved. So maybe part of our class exercise will be improving it with regards to the assignment. Anyway, yeah, that's about it. 2 more assignments left, and then the exam. I don't know. Apparently, the exam schedule is supposed to be out. I could not find it. It doesn't look like they released it. Sometimes they're a couple days late, but yeah. So any questions before we get started? Okay. So I'm going to talk about red-black tree, or no, scapegoat trees. We're going to finish that off, even though we did talk a lot about it, but I think started spinning my wheels at the end. And I think the reason was because we're just being too technical about it. So I just want to talk about a high level of what it is about scapegoat trees that are interesting within the context of what we're talking about, which is, sorted set interfaces implemented by binary search trees, right? So, yeah. So if you recall, the idea behind a scapegoat tree is that it's going to be roughly balanced. And it turns out, in terms of what roughly balanced means, is that you can have something that doesn't really look that balanced, but it still performs quite well. It's still much, much better than linear. And we've seen in the past how things like trees and random binary search trees, we can use randomness to achieve that sort of that balanced tree. But with scapegoat trees, we do something more explicit. We actually rebuild parts of the trees when we find that they're too deep, right? When they get too high. So the first thing I want to talk about is, well, this concept of the idea of a tree being too high, and it's being related to it being unbalanced, right? So what do we say or what do I mean when I say unbalanced? Well, if I look at a subtree, let's say this subtree rooted at the node here with the 7, you can see that the left subtree has a lot more nodes than the right subtree. In fact, the right subtree is empty, right? The right subtree has a nil node, but 0 actual data containing nodes. Okay, so that's what we mean by unbalanced. And so there's a relationship between how hot a tree is, which, as we know, add and remove both depend on this find operation. And the find operation on a binary search tree is related to the height. So that means that we want to keep our height as low. Sorry about that. I don't know how much you guys missed. Oh, right. Okay. So it's this relationship between if a tree is unbalanced, it can be high, and if it's not unbalanced, which means that basically the number of nodes in my one subtree is not too much bigger than the other subtree. And if that's the case, then we can bound the height, right? So that's the entire idea. Besides the restructuring, which we talked about, right? We're going to start at a node that's unbalanced and rebuild the entire subtree. Right? So we gather all the nodes into an array, and then we rebuild the entire subtree as balanced as possible. So that was the one thing that we looked at, but I'm okay with that. But this idea that an unbalanced subtree, or if a tree is high, it must be unbalanced somewhere. That's the other idea that the scapegoat tree illustrates nicely. All right, questions so far? Okay, so the whole idea behind the scapegoat tree is that if we find we add a node and that node, the depth is too high, which means the height of my tree is too high, then I am guaranteed to find an unbalanced node somewhere up the tree, right? So let's see here. Yeah, and there's a lot of math behind this, but I kind of want to take a step back from the math and just talk about conceptually what's going on. So the argument is I'm going to add some, where do I do that? Here we go. Okay, so I've added 3.5 to this scapegoat tree, which before was fine. But now I see that my depth is too much. Specifically, I have this log base 3 halves of q, where q is at least n, right? So the only reason why we have a q and an n is because we want to, q basically keeps track of deletions, right? So once we remove too many things from the tree, we rebuild the entire tree. So that's the idea behind the q, but it's really just a proxy for n. It's a proxy for the number of nodes in my tree. So log base 3 halves of q, you can sort of think of it as log base 3 halves of n. And our claim is that if the depth is, or the height of my tree becomes too large, then at some point I have an unbalanced subtree. Right? So we're going to talk about it from a couple different perspectives. One of them is the following. So I added a node. It turns out it's really deep. It's so deep that log base 3 halves of the number of nodes is less than the depth. So let's say, for the sake of argument, that there was no unbalanced, we could not find a scapegoat, right? So the scapegoat is, again, a node like 7 that is deeply unbalanced. The right subtree is a whole lot larger than the entire tree. Well, not larger, larger than the right subtree for sure, but we usually compare it to the entire tree. Right, so it's 3 dot the size, 3 times this is at most twice this. Or sorry, is greater than twice that. Okay, so this is, this means it's still roughly balanced, but once that is no longer true, then we found the scapegoat. So we found a node that, 3 times this is greater than twice the entire tree. So that means it's deeply unbalanced. And if we can't find it, so we're going to assume that we can't find a scapegoat in order to prove that the scapegoat exists. And sort of a backwards way to prove that would be something like this. So assuming there's no scapegoat, that means that this ratio of 2 times, 2 times size of W parent, where W parent is the scapegoat, over 3 times the size of W, where W is the child. This is greater than 2, sorry. I better double check those numbers. Anyway, there's a ratio. And what that means is that every time I take a step down into one of my children, I can guarantee that, let's say I take the opposite path from root to leaf. So every time I take a step down, I can guarantee that the subtree that I'm stepping into is at most 2/3 of the entire tree. So every time I step down, that means I'm reducing the size of the subtree by at least 2/3, right? So starting at 9, and I'm taking a path to 3.5, that means that if I step down into this subtree, it's not that big compared to this subtree, right? So that's the whole idea behind this ratio. As long as that ratio is maintained, basically I have a balanced tree. So as I go down, every time I take a step into my left child, the size is reduced by at least 2/3. So here, this subtree is at most 2/3 times n, right? And then if I go down again, it's not really true in this case, but this is 2/3 squared times n, right? In this case, 8 would be unbalanced, but we could imagine a case where this was actually roughly balanced. So basically, if I look at the entire tree rooted at 8, and I look at the subtree rooted at 7, the subtree rooted at 7 is at most 2/3 of the size of the subtree rooted at 8. Okay, so we reduce by a constant fraction each time we step down. And if there is no scapegoat, then this is always maintained. This constant fraction as we step down keeps going. So in the next level, it would be 2/3 cubed times n is the maximum size of the subtree. And at this level, it would be 2/3 to the 4th times n is the maximum size of the subtree. And what happens is that we're reducing it by 1/3 each time. And if we do that, there's no way we can get this deep, right? If we reduce it by 1/3 each time, then by the time we get to this node, the size of this node would be less than 1. So size of whatever the node is at 3.5 would have to be less than 1 if there's no scapegoat. Okay. Maybe this is not I sort of claimed it was going to be less math, but it's just less formal math, I guess. Right, so if we reduce by a constant fraction every time we step down, that limits how deep we can go in the tree. Whereas on the other hand, if there is a scapegoat where at some point that constant fraction is not, is maybe I step into a subtree that's greater than 2/3 of my parent's tree, then I found a scapegoat. But also I have more nodes, so I can get deeper in the tree, still maintaining this ratio. Okay, I don't know. Maybe that's easier to understand. Maybe. Questions? All right. So at a higher level, basically, if the tree is bounded by height, it's roughly balanced. If the height becomes too big, then you know it's out of balance somewhere, basically. And that's the idea behind this test. This test tests for exactly that. Basically, it says that the depth is too much, which means there must be a scapegoat somewhere. Mathematically, we can prove it, although I'm not going to. And then we looked at this tree. And so how we implement it is not going from the root down to the leaf. We start at the leaf and we go up looking for the scapegoat, right? We know a scapegoat exists, and basically it's the ratio of, the size of this tree compared to the size of this tree. So the size of one node over 2 is 1/2. In this case, I look at 2 over 3, so that's 2/3, but it's not greater than 2/3. This node is 6 in total, but this subtree is 3, so it's 3/6. But when we get to here, the entire subtree is 7. Sorry, the entire subtree rooted at 7 has size 7, and the size of its child is 6, which is greater than 6/7 is greater than 2/3, so we found the scapegoat. Right, so 7 is the one we rebuild into, perfectly balanced a binary tree as we can. Okay. Questions? All right. So add, yeah, so we'll do a little bit of analysis, but all of the analysis is basically related to the height of the tree, right? Once we've bound the height, then we've bound the length of any search path, including the search path, in order to add an element. So to find where to add the node is big O of log base 3/2 of n, right? And that's because every time you step down, it's at most 2/3, right? The size of your subtree is reduced by at least 1/3. Yeah. Okay. So to add is bounded by the height, which is, at most our height is going to be off by 1, right? So we added a node, maybe this is log base 3/2 n plus 1, but that's still big O of log base 3/2 of n. Finding a scapegoat, how long does that take? Well, we step up the tree, right? And that is basically big O of the height again, because I'm going to look here, and then I'm going to look here, then I'm going to look here, and then I'm going to look here. But I'm calling size on each of those nodes, right? So how do we know the size of these subtrees? So how did we implement that? Or I don't know, maybe we talked about it, maybe not, but what are some ideas at least? So I get to here, I say, I'm comparing the size of this subtree to the size of this subtree, but how do I know the size? How do I compute it? Right? So, I mean, there's two choices, right? We can either compute it from scratch each time, and we're rebuilding the tree, so maybe that's not a bad option. We can try and store the height, or sorry, the size at each of these nodes, but then we got to be careful every time we add something, we have to change the size, but also we're going to rebuild at some point, and that's going to affect the size. We could do that. It would be a little bit harder for us as a programmer, but I don't think it's impossible. In our implementation, in the ODS implementation, though, we do a traversal, right? So I want to find the size of this. Basically, my size algorithm is something like this. The size of u is 1 plus size of u dot left plus size u dot right. So we compute it from scratch each time, right? We can save a little bit of information. We could save ourselves some trouble by, every time we step up, we remember the size from here, but we still have to compute the size of each node along the path until we find the scapegoat. And we do that really from scratch. We do a traversal. So if I want to find the size of this node, I start by going down here. The size of this is 0. The size of this is 0, right? There's a if nil statement in here. I return 0. And then it's 1 plus 0 plus 0 is the size of this one. And this is, of course, size 2 and size 3. So finding the scapegoat, just the walk up the tree is easy, but calling size on every node along the way, that is expensive. Okay, so we'll talk about exactly how expensive, but each call to size, of course, runs in big O of the size of that node, right? So each call to size is a complete traversal. So if I call size on 3, I visit every node in the subtree. So it's big O of size of that node. And I'm calling it for every single node up the tree. That seems like it would be a lot, but it's actually not that bad. We'll talk about that in a minute. How much does it cost to rebuild? Well, rebuild, again, is just the size of the subtree, right? I'm rebuilding at 7. That requires a traversal. I gather everything into an array, and then I basically divide the array in 2, but I can do that with math. I don't have to, I revisit each node once more in order to make it the root of its own subtree. So rebuild at Z is O of the size of Z as well. Okay. All right. We'll talk a little bit about remove, and then we'll look at that size thing, and then we'll leave scapegoat trees behind. I don't know. There's too much math, I think, for this. So when I remove something from my scapegoat tree, it of course never increases the height, so I kind of don't have to worry about that. When I call remove and I find something and delete it, I decrement n. I have one less item in my tree. Q is unchanged, right? Q is sort of the marker of how many removes or how many remove operations since my last rebuild, right? That's what Q is. So if Q is greater than 2 times n, in other words, if I've removed half of my tree since the last time I rebuilt it, then I'm going to rebuild it again. At that point, it's just a big mess, right? I could have removed, I could remove this guy, and now it's still base, the height is still log base 3/2 of Q, but now my n is getting less and less than Q, so it's still logarithmic, but it's a logarithmic of a bigger tree that used to exist. But at some point, I just delete too many things. I'm going to lose the bound on the height of my tree, so I just rebuild from scratch. All right, so the other aspects of remove, I find a node to splice. Recall, if I'm removing, well, let's say I'm removing 3, then I'm going to find the in order successor, which is I'm going to go down to 5. I'm going to replace 3 with 5, and then I'm going to delete that. So I have to walk all the way to the bottom of the tree, which is big O of the height of the tree, which is log base 3/2 of n, and then a constant number of pointer manipulations, right? Just to delete this and to assign this value to my node. Okay. All right. So this is the proof that I sort of started with talking about. Basically, every time we go down, the size of the child decreases by a constant fraction, and if you keep doing that, you're limited into how deep you can go before your size gets less than 1. The other, that actually gives I'm going to just give a brief overview of the proof. So all of the calls to size, if I sum them up, are at most the size of the scapegoat times a constant, right? So if I add something here and then I go up, I compute the size of my parent, and then I compute the size of this one, and then I compute the size of this one, then I compute the size of this one, and if I sum all of those calls up, basically all of those calls are at most some constant times the size of this entire subtree. Right? So even though I make multiple calls to size and I'm sort of repeating a lot of work, because the tree is balanced, I get that same effect that I did before. Whereas basically it's a sum of a geometric series, which sums to a constant. So yeah, all my calls to size are a constant times this subtree. All right, let's leave scapegoat trees behind. They are, I don't know. They're fun, they're good, but the math, it's just too much math, not enough hand waving, I guess. But Scapegoat trees perform pretty well. Any sequence of M, add, and remove operations. Yeah. Okay. Sorry, one more thing before we go. And again, I'm going to hand wave it a little bit, but rebuilding my tree is amortized, the same as before. Right, so every time I rebuild, I spend M log M time rebuilding after some sequence of M add or remove operations. And what that means is that, well, each add and remove takes log n time. So if I have M add and removes, those in total will take M log n time. And when I rebuild, it's at most M log M time to rebuild. Okay, I'm not really going to get into the proof of that, but it is similar to the amortized analysis that we did before with stack arrays and things like that. But yeah, so it works based on a credit scheme, which is kind of an interesting proof, but yeah. Yeah. All right. So scapegoat tree, if we ignore all the rebuild operations, we can all our add, remove, and find operations operate in O of log n time, right? Because the height is bounded. But also, the amount of time we spent rebuilding is proportional to the amount of time we spent in add and remove. Basically, that's the idea behind this. Questions? Okay, let's get away from this before it's just pure math at this point, and I really don't want to get into that. But let's look at how well this performs. So we have looked at other sorted sets. We've looked at skip lists, and we've looked at treeps, and we've compared them. The ODS library also has a scapegoat tree, so we're going to run that and see how that compares. So we saw that, in general, skip lists, in a lot of cases, perform faster than treeps. Sorry, treeps perform faster than skip lists, except for a few operations. So let's see how scapegoats compare. Okay. No. Okay, what is it? The name of this test is sorted set test. Okay. So just random insertions. The scapegoat tree is, they're all comparable, I guess. For the contains operation, the scapegoat tree is the fastest. So it's on average, at least in this case, more balanced than the treep tends to be, where treep is basically a random binary search tree. And faster than the skip lists. They're both faster than the skip lists. Removals, scapegoat tree is also very fast. Yeah, I'm not sure exactly why, except most of the removals don't involve any reconstruction whatsoever. Finding a head set, of course, skip lists are the easiest thing to chop into two separate lists. If I want to return a partial treep or a partial scapegoat tree, it takes a little bit longer, but it's faster than the treep, but not as fast as a skip list. iteration, I mean, they're all pretty fast, but the scapegoat tree is, I mean, that shouldn't really matter, but the height might have something to do with that. Sequential insertions, the scapegoat tree is very slow compared to the other two, right? So that means I'm inserting in sequence, which means that what's going to happen basically is I'm going to when I do sequential insertions, what happens is I get a tree that looks like this, and on a scapegoat tree, of course, it's going to be rebuilding quite often, right? Because it's going to, quite often, the depth is going to exceed the bounds that so then it's going to have to rebuild it, and then it's basically making it as deep as we possibly can in as short a time as we possibly can. So our scapegoat tree does not respond well to that. Sequential contains, it's fine, it rebuilds. There's nothing else it really needs to do. Headsets, yeah. So I don't know. So anything that requires, right, if I'm adding things in sequence, that's bad for my scapegoat tree because I have to do a lot of rebuilding. But it is better balanced than a tree on average. As long as I don't have to add and remove too many things, scapegoat tree might be a good choice. All right, questions? Okay. Forget about scapegoat trees. I really love scapegoat. It was one of the first lectures I ever gave, actually, was on scapegoat trees. So I kind of, there was a soft spot in my heart, but like, as I go back over it, it just seems brutal math for almost no, I don't know, there's nothing really special about it, right? There's other trees that perform a lot better. So one of them that performs really well is the red-black tree, right? Red-black tree is actually in production in a lot of places. We'll talk about red-black trees, but we're going to start by talking about 2,4 trees because 2,4 trees are in some sense isomorphic to black trees. Red-black trees are somebody's attempt to imitate a 2,4 tree in a binary tree. So a 2,4 tree is not actually a binary tree, as we'll see. And the ODS library doesn't actually have an implementation of a 2,4 tree, although it has an implementation of a B tree, which is similar. So we'll talk a little bit about that, but yeah, our quote of the day: if you cannot grok the overall structure of a program while taking a shower, you're not ready to code it. So grok means, you know, deep understanding of something. And yeah, that's, I mean, I know when we start out, everybody sits down to code and then just sort of figures it out as they go, but it does pay dividends to think about how you would solve the problem and sort of the problems you would run into. Even though when you sit down to code, you're still going to run into problems. It's not going to work out the exact way that you thought, but it is worth doing. So as mentioned, we are going to talk about red-black trees, but it's worth taking a look at 2,4 trees, both in their own right, as they are in some sense a B tree, but also to help us understand red-black trees, which are kind of opaque. So this is a red-black tree, or sorry, this is a 2,4 tree. You can see it is not a binary tree, but it is isomorphic to a binary tree, which means that in some sense, we have this same structure in a red-black tree, but maybe it's represented a little bit differently, right? But functionally, it's the same. So same structure, even if they're implemented differently. 2,4 trees are examples of, more broadly, a multi-way search tree or an M-way search tree. And yeah, also related to B trees, which are, you know, red-black trees are in use in a lot of places like Linux and probably your sorted set Java implementation, I'm guessing, would be a red-black tree. But B trees are used for reading and writing from disk, and figuring out how to store data on external storage. So they're very useful for that. Okay, so an M-way search in general, Each node can store up to m-1 values, and each node can have up to m children. And actually, there's a tighter relationship to that. So we can see here, this node contains 3 values, and it has 1, 2, 3, 4 children. Okay, and so we'll talk about how those are organized. This is basically a generalization of a binary tree. Each node stores some list of elements in order. So here we have 3, 10, 20, 30, and they are in sorted order. Okay, and then yeah, an internal node with k children. Yeah, this is right. So given that I have an internal node here, it's storing 3 data items in order, then the children are, right, I have this is data 0, 1, and 2, and then I can say this is child 0, this is child 1, this is child 2, and this is child 3. And the idea is that, well, my child 0 is going to be less than this data item, or less than or equal to if we're allowing duplicates. We will assume for now that this is a sorted set. So we don't allow duplicate, even though you'll see in some of the examples I did put duplicates accidentally. It doesn't hurt the implementation. So everything in this subtree is going to be less than 12. Everything in this subtree is going to be between 12 and 15. Everything in this subtree is going to be between 15 and 18, and everything in this subtree is going to be greater than 18. Okay, so that's how these M-way search trees work. It's sort of like a binary tree, except I'm allowed to store more things in each node, and then every time I add a node, I also add another child. Right? So if I started out with a binary tree, and then I add a new data item, I have to add another child. So yeah. All right, questions on that? Okay. So given just these properties, it's of course easy now to perform a search in an M-way search tree. So I'm going to start here, and let's say I'm searching for 16. So I'm going to do a linear search on this current node, and I'm going to stop as soon as I see something that is greater than or equal to 16. So I look at 10, well, 10 is less than 16, so I have to go a bit further. I look at 20, 20 is greater than 16, which means that, and 20 is not equal to 16, but that means if 16 exists, it's down this child. Okay, so I do a linear search to find, I stop at the first value that's greater than the thing I'm looking for, and then I proceed down that child. If I found the thing I'm looking for, I just return it. That's great. If I said find 40, well, obviously 40 is greater than 10, greater than 20, greater than 30. Well, in that case, I would proceed down this child. Okay. So from node to node, that's basically how we do it. And then just keep repeating. So find 16. I compare it to 10, 16 is greater than 10. I compare it to 20, 16 is less than 20. So I go down this child. I start at the beginning. 12 is less than 16. 15 is less than 16. 18 is greater than 16, so I go down this child, and then I found the thing that I'm looking for. Okay, so that's an M-way search tree, and that's basically how you search. Almost the same as a binary search tree, just a little few extra steps. Right? So questions? Okay, so similar to a binary tree, of course, the search path of an M-way tree is bounded by its height. As long as the number of elements I store is bounded by some constant, right? If I'm storing at most 3 elements per node, then of course, at every node, I have to do up to 3 comparisons, and then I take one step down the tree. So it's going to be, basically 3 times the height of the tree. That's the number of comparisons I have to do before I find what I'm looking for. Within a factor of n, yeah. Sorry, 1 second. So the length of the search path is at most m times the height, where m is the number of, m minus 1 is the number of nodes I can store, number of values I can store in any given node. So a 2-4 tree is a 4-way search tree with a couple of other properties, right? So this search path works on a 2-4 tree. Also the idea that, when I can have at most 3 pieces of data and at most 4 children per node. And it's called a 2-4 tree because, because any given node can have 2 children, it can have 3 children, or it can have 4 children. That's why it's called a 2-4 tree. Okay. All right. So all of the properties of m-way search trees apply to 2-4 trees. But in addition to that, all of the leaves of my 2-4 tree are at the same depth, right? So you'll notice here that these are the leaves. If you look in the textbook, the leaves are represented as nil nodes, right? I could draw nil nodes in here. So I could say this is nil, the left child is nil, and the right child is nil. And here, and here, and here. I could draw all those in, but I just left it out for this. I don't think it's that useful for 2-4 trees. It's a little more useful for red-black trees. Regardless, the leaves are always at the same depth, right? So here, all the leaves are at depth 2. And of course, what does that say about the height? Well, in this case, the height is 2. And that is, true anywhere. Any root to leaf search path is exactly the height, maybe times, m minus 1. Okay, and we could take this a step further. So the idea is that the height of this tree is log of the number of nodes, right? At most log base 2 of n times some constant. Right, so this is, again, we talked about with the scapegoat tree, how if we can bound the height, then it's going to be, or if it's roughly balanced, we bound the height. And of course, the height is everything in terms of search path. So for us, we want to show a bound on the height. If all of the leaves are at the same level, and every time, so if my tree has a height h, the number of leaves is at least 2 to the h, right? Because I start with at least 1 piece of data here, and then in the next level, I have at least 2 pieces of data, and in the next level, I have at least 4 pieces of data. And so my height here is 2, and the number of leaves is at least 2 to the power 2, or 4. You can see, actually, in this case, it's a lot more than that. But at the very least, a valid 2-4 tree of height 2 would look like this, would have at least this many nodes in it. Okay, so that's the sparsest 2-4 tree I could have that has a height of 2. This one has a lot more, but yeah, questions? The number of internal nodes is at least 2 to the h minus 1. This is sort of, right, if I have a binary tree that is a complete binary tree, well, here I have 4 leaves, and I have 3 internal nodes, right? So if it's complete, the number of leaves is always 2 to the power h, and the number of nodes that are not leaves are 2 to the power h minus 1. So that's something general about binary search trees, and we're using that to show there's a bound on how high this thing is. Right? So what that means is that if I take 2h leaves plus 2 to the h minus 1 internal nodes, that gives me 2 times 2 to the h minus 1, and 2 times 2 to the h is 2 to the h plus 1 minus 1. Right? So that means the number of nodes in my 2-4 tree that has a height of at least, has a height of h, has at least 2 to the h plus 1 minus 1 nodes. And then if I take the log base 2 of both of those things, so this means that 2 to the h plus 1 minus 1 is at most n, and the log of 2 to the h plus 1 minus 1 is at most log of n. And then this is, we can say, log of 2 to the h. Sorry. Yeah. And of course, log base 2 of 2 to the h is simply h. So this is h is at most log of n. So that means the height of our 2-4 tree is bounded. Okay, I don't know. We've done similar computations in the past, but basically if I at least double the number of nodes on each level, then the height will be bounded by a constant, or by the height will be logarithmic in the number of nodes. All right, questions? All right, so this is just to prove that our height is logarithmic, which means that all of our find operations on 2-4 trees will take log base 2 of n time, or log base, at most log base 2 of n time. And then maybe times 3, because we have to search through 3 items for each node that we encounter. Okay, but that's not bad. That's pretty good, actually. All right, so we are going to implement the sorted set interface on this 2-4 tree. So we also want to implement the add and remove. Yeah, so we're gonna, for this one, there is no code in the ODS library, and we're not really gonna write code for it. We're just gonna look at the algorithms behind it. Add and remove methods involve complex restructuring sometimes. Right? Sometimes we're lucky, we can add something or remove something that doesn't affect the tree whatsoever. Other times when we add and remove, it causes problems, and we're going to see how to solve them. Right? And one of the reasons why is that as complicated as this is, it's simpler than red-black trees. And so we're going to use our knowledge here to help understand red-black trees a little bit better. Okay. Right, so restructuring a 2-4 tree requires splitting nodes, merging nodes. We're going to see what those operations entail. And sometimes we have to borrow from a sibling, right? So there are certain, some of the things I have to maintain. If I have 2 data items here, I need to have 3 children. So that means, I got 2 19s there. So that means if I got a lot of 19s. All right, this is not a great tree, right? So this is violating the, I don't know what I did there. I must have, I think I copied and pasted these, and then I was going to change them, and then I forgot. Sorry, imagine these are good numbers, but if I have 2 data items here and I delete this guy, well, now this is no longer valid. I need to have 3 children for these 2 data items in this node, and I only have 2, so now I have to do some restructuring. So we're going to see how we can handle all of those cases. So we're going to have to borrow, and this is going to involve a type of rotation, which we've already seen in treeps. So yeah, we're going to use basically similar rotations, but in a 2-4 tree. And all of these operations, we're going to see them again when we look at red-black trees. We're going to see how to do the exact same thing in a binary tree. Okay. And again, this is, I'm not going to write down the algorithms. Well, maybe I'll try to write up something a little more formally later. But we're just going to go through the operations. We're going to see what problems they cause. We're going to see when it's easy. We're going to see when it's hard. We're going to see how to solve the hard ones just by looking at the pictures, though. So let's look at the add operation, and let's look at this 2-4 tree. Sorry, any questions before we get started? It's going to get a little complicated here, so if there's something you don't understand, now would be a good time to bring it up. Okay. Add 27. Well, as before, I want to do a find operation for this number 27. Right? So if I go back, I want to find 27. Well, 20 is less than 27, so I look at the next value. 30 is greater than 27, which means I'm going to go down this child. And then down here, there's a short list of at most 3 elements. And I want to keep it in sorted order, but since it's only 3 elements, that's really simple, right? I just look, where does 27 go here? Well, it goes at the back. If it went to the middle, I would have to shift at most 1 element, or, whatever we wanted to do, even just using the most basic list implementation. There's only a constant number of operations to keep 3 items in sorted order. It's not that hard. Okay, so that's, and at this point, if there's room at the leaf, we insert the element. So at this point, I found a node with only 2 data items. I'm allowed to have 3, so I could add 27 to this node. And now everything is still fine. I haven't violated any 2-4 tree properties. And in particular, I still have all leaves at the same depth. Okay, so that's easy. Do you have questions on that? All right. Let's say I make another call, add 29. I try and do the same thing. I try to find 29. Of course, I'm going to go down this path. And I'm going to try to add 29 to this leaf, but I'm only allowed at most 3 data items in this leaf. If I try to add a 4th, I'm violating this M-way search property, or M-way search tree property, right? I'm only allowed to have 3. Okay, so what do? Well, I'm going to do what's called a split operation, right? So I'm going to take this leaf, I'm going to split it in 2, right? So I wanted to add 29 here, but this node is too big. So before I add it, I'm going to perform a split. I'm going to split my node into 25, 22, and 27. 22 and 27 are going to be the leaves. And 25, I'm going to send up to the parent. Okay, so I'm going to make room in the parent. It's actually, basically, this was previously the child between 20 and 30, which means 25 will go between 20 and 30. And yeah, so 25 goes up here. And then these 2 become children of that new node, right? And this split does not violate any of the M-way search tree properties, right? 25 is between 20 and 30, which is perfect. 22 is between 20 and 25, and 27 is between 25 and 30, right? So now I still have a nice 2-4 tree. I just had to do that 1 split operation. All right. Of course, what's the problem? Maybe I already had 3 elements in my parent, and now I'm sending a 4th one up there. And so now I have to recursively split the parent, right? And this can go all the way up the tree, as we will see. But any questions so far? Is that a question? like if there was two? So the child can only be, so yeah. So and I think I've just defined it. Maybe I wasn't clear enough about, right? So this is a four-way search tree, which means I can have at most 3 data items in any node. Yeah, so 3 is the maximum. It's four-way because I have 4 children. Right, so yeah, that's I probably didn't emphasize that enough. So four-way search tree means 3 data items and 1, 2, 3, 4 children. Right, other questions? It's great though, it's finally a question. It's been a long time. But a long summer of, well, questions after class. That's okay too. All right. Okay, so I add, yeah, I might have to recursively split my parent. Here I added 29, and of course I just follow the search path. Go down here, I add 29 to this node. Etc. So my add operation for add x, I'm always adding at a leaf. If there's no room in the leaf, I split the leaf and I send the middle element up to the parent. And then I might have to recursively split the parent at that point, which we're going to see an example of that. We just haven't gotten there yet. How do we have 4 children for 3 nodes? So they're not really nodes. This is a single node with 3 data elements. And if we think about it, 20, 15, and 22, right? That's a binary search tree node, right? So 15, everything in the left subtree is less than, so everything in here is less than 20, everything in here is greater than 20. So now I'm just kind of generalizing that. I'm making my node be able to handle another data element. So here, 24. But as soon as I do that, I have to add a third child. So 25. So you can see a binary search tree. I have 1 data element and 2 children. For a 3-way search tree, I have 2 data elements and 3 children. And for a 4-way search tree, I have 3 data elements and 4 children. So every time I add another data element, I add another child. But there's always 1 less piece of data in my node than there are children, right? And that's important because we want to, it's going to send us down to a subtree that is a lot smaller than, right? I'm eliminating basically 3/4 of my search path at this point, right? So if I do a search down here and I go to this subtree, well, I can ignore everything in here, everything in here, and everything in here, and I'm searching around a reduced search space, which makes searching fast, right? So that's the idea behind it. I don't know, hopefully that kind of answers your question. Other questions? Perfect. Okay. All right. So always add at a leaf, split the leaf if there's no room. We send the middle element to the parent. And then I treat that as if I'm adding to the parent. I might have to recursively split, as we will see in the next example. Is it this one? Yeah. So here I'm trying to add 10 to some 2-4 tree. Most of it's not pictured, but so 10, of course, my search path goes through 5 down this child, and then, you know, it's greater than 6, but less than 11, so I go down this child, and I add it to the end, and we can see that now I have 4 data items. That's not legal. There are other ways to handle this, by the way, right? We could do preemptive splitting, but we'll get to that later. So I have to split this current node that I'm at. I split 8 up to my parent. Right? 8 is the middle node of all the data was there before. So I'm going to send that up. And now I have my parent node has 4 data elements. So I want to split it. And I kind of want to look at, I want to ignore 8. And I just want to look at what was there before and send the middle element up to the parent. So I'm going to send 11 up. That splits this node into 6 and 8 and 15 over here. Again, though, now my root has too many data elements, so I'm going to split it again. 11 was the one that I added, so 20 is the one that I'm going to send to the parent, but there is no parent, so 20 is going to become the new root of my 2-4 tree. Okay, so when I add something to the leaf, it could cascade all the way up the tree, and at that point, I've increased the height by 1, right? But because it happened at the root, the height is increased for everyone. So all leaves now are at a new depth that is 1 more than the previous depth. All right, does that make sense? Any questions? Okay. All right, so let's add. Add is kind of easy. It's just a split. Split's not that hard, conceptually at least. And you'll see it's even easier on a 2-4 tree, or sorry, on a red-black tree. Remove is a little trickier. Oh, there really are only 2 cases that are tricky, and they are sort of similar, but yeah, let's look at the basic remove. So I have a 2-4 tree I call remove 25. If it's a leaf, well, I'm all set, right? I just look for it. 25 goes down this child, and then it goes down, well, 25 is actually less than 26, so it goes down here. And then I find 25 here. I just delete it. This is a leaf. I delete it from the leaf. And in this case, there was already 2 data items there, or sorry, already 3 data items, and now there's 2, so it's still legal. Nothing about the shape of this tree violates any properties. That's the easy case. I find the thing I'm looking for, it's at a leaf. That leaf has more than 1 data item. I can delete it, and that's it. Of course, there is this problem hanging over our head. What if I get to the leaf and that's the last one? Now I got some problems, but we'll talk about that in a minute. If X is not a leaf, right? Maybe I call remove 20. Do I call remove 20 here? Yes, remove 20. Well, then we're going to do very similar to what we do in a binary tree when we want to remove something. Or sorry, a binary search tree, is we're going to find the in-order successor. Right, so if you recall, in a binary search tree, to find the in-order successor, if I wanted to remove X, then I take 1 step to the right, and I go left as far as possible. And then once there's no more left child, then this becomes my in-order successor. Right, so I still have to go to the bottom of the tree. I find the in-order successor. Let's call that Y. Y gets replaced here, and I can delete this guy. Since they only have 1 child, we do the adoption thing where the parent adopts the child, and that node is spliced out of the tree. Okay, so that's how we do it on a binary search tree. 2-4 trees are almost exactly the same. I remove 20. Well, I'm going to go into the right child of 20, which is this one. Okay, not the far right, not over here, but just the one here. I want to find the lowest number that's greater than 20. Yeah, basically the lowest number that's greater than 20 that's in our tree. Once I get here, I'm going to do the same thing I did before. I'm going to travel, I'm going to go as far left as I can, and I'm going to keep going to the far left until I reach a leaf. Okay, in this case, my leaf is right here. So, and then I'm going to find the leftmost piece of data in that leaf, which is 21. Okay, so very, very similar to finding the in-order successor in a binary tree, but in this case, our in-order successor will always be at a leaf. Is that right? Yeah, I guess that's true. Interesting. Sort of, I knew that, I knew that, but sort of, when you think about it, that's kind of weird because that's not necessarily true in any other binary tree. But yeah, so I have 20. I found the in-order successor. I'm going to copy that into this location, and then I can delete this node from my tree. It's a leaf. So and in this case, this leaf node has 3 pieces of data. So yeah. And of course, it's the lowest y such that y is still greater than x. You can also do the highest y such that y is still less than x, right? So I could have gone down this, taken a left, and then gone as far right as I possibly could until I reached a leaf, and I could use that as the in-order successor as well, just as sort of a pre-order successor. Okay. Once I find the successor, I replace x with y. So this is my x, this is my y. Delete y. Do I ever do this? All right. Well, apparently I have a lot of slides for this, and I guess I mixed them up. So I replace 20 with 21, and then I just delete 21 off the tree. Okay. So that's straightforward questions. All right. The successor x operation. Well, this is what we just went over. Basically, I step into the right child of 20. That's this. And then I go take the far left child until I reach a leaf node. So I go down here, and if this had another level, I would follow that until I hit a leaf, and then I would take the leftmost value or the lowest value in that leaf, and that's our successor. All right. Oh, I did do it. Perfect. So yeah, I replaced 20 with 21. I didn't actually have to switch them, but and then I deleted that. Okay, so those are the easy ones, right? If it's at a leaf and there's more than one piece of data in that leaf, I can just delete the piece of data. If not, if it's not in a leaf, I find the in-order successor, and then I'm deleting from a leaf. Okay, so whether or not the thing I'm actually deleting is in a leaf, structurally, I'm deleting something from a leaf in a 2-4 tree. Okay, either the element itself or the successor. So from here on out, for the remove operation, we're to assume we're deleting from a leaf. All right, so now remove 9. Well, I'm going to follow the search path for 9. And I found 9, and now I'm going to delete it, but now my leaf has only one element in it. Yeah, so what happens if we delete the last piece of data in the leaf? Right, so, so I'm deleting the 9, trying to coordinate all these diagrams with the slides. They're not quite lining up, but hopefully you get the idea. So I'm deleting this. This causes a problem because I have to have a child down here, right? That's sort of one of the rules that I'm maintaining. So, but I'm going to look at my 2 siblings, right? I'm going to look over here. That is a single piece of data in a leaf, so I cannot borrow from that sibling. But I look in this sibling, right? Sibling is basically we have the same parent. Both of them have a parent of 10. This sibling, they have 2 pieces of data, so I'm going to borrow 1 piece of data from that sibling. Okay, and how I'm going to do it? Well, I can't borrow it directly, right? I can't just take this, let's say 11, and put it over here, because now 11 is less than 10. and this is I'm violating that M-way search tree property, right? I can't search properly anymore. Whatever's here has to be between 8 and 10, but I can do sort of a rotation, right? So I'm going to actually borrow from my parent. I'm going to take this 10, and this 11 is going to go up and replace it. And that's how I'm going to maintain that M-way search property, is this sort of a rotation. So I'm actually borrowing from my parent, and the parent is borrowing from the sibling. And then in the end, I end up with 10, which used to be in the parent. It's between 8 and 11, and 12 is greater than 11. So all of my properties are okay, right? So if I can borrow from a sibling, I do that. Questions? Okay. So yeah, this is a sort of a rotation in a 2-4 tree. What if I do not have any siblings to borrow from, right? So I call remove 13. I'm removing this. You can't see it there, but it's the only piece of data. I look at my sibling. There's only one piece of data there. I can't borrow from them either, right? So in this case, I can't borrow. So I'm going to borrow from my parent again. I mean, I guess we always do that. But then I'm going to just merge with my sibling. Okay, so I take 12 down from my parent. It's it's the proper successor, and I can merge it to my sibling. And now I have one node with two pieces of data. And the parent node has one less piece of data and one less child. So I've still maintained that, two pieces of data, 3 children. So that's still valid. So if I can borrow from a sibling, I borrow from a sibling, or really, I always borrow from my parent, but sometimes the parent then borrows from the sibling. If I can't borrow from my sibling directly, I borrow from the parent, and then I move in with the sibling, right? This is sort of later in life when you're trying to save money, you borrow money from your parent and move in with your brother or sister. All right. Questions on that? It's a metaphor. This process can also cascade up the tree, right? So similar to how we could split all the way up the tree, this borrow from a parent and merge operation can go all the way up the tree. What do we got? So let's finish that and then take a break. So yeah, let's go to this one. Okay, so this is a valid 2-4 tree. Not all of it is drawn, but we're going to remove 12 from our tree, and we're going to see how this cascades up the tree and eventually reduces the height of our tree by 1. Okay, so I remove 12. I look at my sibling. I have only 1. The sibling does not have any spare data. Does not have any spare money to give me. So now I'm going to borrow from my parent, right? So deleting 12, maybe it was an in-order successor. Maybe I'm removing it directly. I borrow from my parent 13, and I merge with my sibling 15. However, whereas before there used to be data, we did this exact same operation before, but the parent had 2 pieces of data, and so I borrowed one of them, and then I moved in with my sibling. In this case, when I borrowed from my parents, they were left homeless, right? Not really, but this node is now empty. So now I have the same problem again. So I merge 13 and 15, but I have to do something with this empty node. So if I can borrow from my sibling, I do that, right? In this case, though, I can't. My sibling has only one piece of data. So again, I'm going to borrow from my parent, this time 11, and I'm going to move in with my sibling. Now my aunts and uncles are moving in together. And then now my parent is, again, my grandparent this time is out of money. So they're going to borrow from their parents, which is 16, and move in. Move in with their sibling. And then at this point, the root is empty. So when I merge 16 and 30, that becomes the new root, and the height of my 2-4 tree is reduced by 1. Okay, so our 2-4 tree will grow and shrink, but only at the root, and only as a result of either splitting all the way up to the root or borrowing from the parent and merging with the sibling all the way up to the root. All right, questions? Okay, so let's take a little break. Come back 105-ish, maybe, it's not really an exact, but somewhere around there, come back and we're almost done talking about 2-4 trees, and then we'll move to red-black trees, and we'll see how they're basically the same thing, but implemented in a binary tree. But yeah, I'll see you guys in about 10, 12, 15 minutes. Okay. All right, so it's 105, so it's kind of close enough. So I guess, yeah, somebody mentioned you can see the exam schedule. They just changed the interface a little bit. It completely fooled me. But if you go here and show finals, and then of course scroll down to COMP2402A, you can see here. Now, I am very reluctant to actually say the date and time on video, because in the event I get it wrong, a bunch of people are going to show up at the wrong day and time. So there it is. Take a look. Double check for yourself, please. You show up to the correct place on the correct day and time. But yeah, so now you can sort of make plans for the rest of your summer. All right, I wanted to get back to how are we at 2-4 trees? Okay, so before we get back into 2-4 trees, I did add to this sorted set test, I added a Java tree, right? So a tree set from the Java library. I was trying to, I just did a quick Google search about how they implemented it. They don't really give details, and that's sort of, that's par for the course, right? Because that's the thing about documentation, is that if you change anything about the implementation, now your documentation is lying. So a lot of people who write documentation sort of hedge their bets, don't give away too many details. They say it's a balanced tree. Yes. Yes. So are you going to have a practice test for the final exam? Yes. There will be a lot of multiple choice on the final exam, though, right? We're going to mark some will be short answer, like the midterm, and I will give you practice questions for those questions. The multiple choice, I will give you general things to study, but of course, I'm not going to give you a set of multiple choice questions. You'll just have to study the things that are mentioned. So yeah, other questions about the final? I will, as when that practice final comes out, well, let's see. They want the final about 2 weeks before the final exam. So I will certainly have it ready by no later than 2 weeks before the final exam. We'll have a practice ready to go. Yeah. Other questions about the final? All right. So I added a Java tree set, probably a red-black tree, but you can't be certain. In the test, so random insertions, we could see it's sort of comparable to the Scapegoat tree. Actually did a little bit faster. Ideally, you would run this test a few times and average these results, because things like the garbage collector can affect, if the garbage collector goes off during one run and not another, that can affect things. Contains better than a tree, but not as good as a Scapegoat tree. I am really not sure what Java is doing behind the scenes that makes these a little bit slower. Probably something, Java is supposed to be a safe language rather than a super fast language. So probably something safety related. Very good at removals though. We'll see, we'll compare it to red-black trees and see if they beat them. But for now, Comparable on partitioning the tree, iteration, not as good as a scapegoat tree again, but better than a tree. Yeah, so about what you would expect. This contains, though, really fast. Probably, if it is a red-black tree, it has tighter bounds. Does it have tighter bounds on the height? Might have tighter bounds on the height. At least in practice, it's probably on average, the height is maintained better than a scapegoat tree. But yeah, let's all right. So we were talking about 2-4 trees. We talked about find is fairly straightforward. Add is fine. We always added a leaf. Sometimes we have to split a leaf, and sometimes that split operation goes all the way up the tree and increases the height of the tree. If we have to split the root. On the other hand, the remove is a little more complicated if we, right, if I remove something, a leaf, and there's no other piece, if I remove something that's, from a leaf that has more than one piece of data, I'm fine. If I remove from a leaf with only one piece of data, now I'm going to borrow from my parent, and then the parent might borrow from the child, or I might merge with the child, depending on how much data the parent has, right? So although we refer to it as borrowing from the sibling, it really is sort of a rotation that goes like this. On the other hand, if I borrow from my parent, and my parent has nothing left, I move in with my sibling, and then my parent goes looking to find another piece of data, and they either move in with their sibling or they borrow from their sibling, and so on. So those are the main ones. A remove, easy if it's from a leaf and there's extra data. Otherwise, we borrow from a sibling, and if the sibling we can't afford to borrow from a sibling, we borrow from our parent, and we move in with the sibling. All right, so that's it. And that process can cascade all the way up the tree. And then if my root, if I borrow from my parent, the root becomes empty, I move in with the sibling, then the height of the tree is decreased in that case. Okay, so in our 2-4 tree, a find operation runs in big O of the height, and we've shown that the height is at most log base 2 of n. Add and remove both use the find operations. Of course, there's also the restructuring. So just the add and the remove themselves are sort of log n operations, but maybe I have to merge or split and borrow. So how much do those operations cost us? Well, not that much, actually. Every time I merge or split or borrow, it's just a constant time operation. I'm just moving some pointers and maybe copying a bit of data. On a remove, if I have to borrow, then that's it, right? That doesn't go any further up the tree. If I have to merge, that can go all the way to the root, but every time I merge, I go into my parent. So I can only merge as many times as I have levels in the tree. So again, merge, split, borrow. Every one of those operations moves one level up the tree, so they are going to be big O of the height of the tree, right? Yeah, so if I split, it goes all the way to the top, big O of the height. If I merge and it goes all the way to the top, it's also big O of the height. If I borrow, then I'm done, right? I don't go any further up the tree. All right, so for my merge and split operations, there are most height plus 1 of those for each call to add or remove. And there is, I'm sure, either, well, maybe I'm not sure, but I would suspect that they're amortized constant time. Actually, I think they are. And that proof might, where did I see that? Yeah, I think the proof is in the textbook, actually. So yeah, we're not going to go that deep, though. A log n time for each of these is enough. But as it turns out, even the split and the merge, they can't happen that often, right? I have to add a whole bunch of things before I split all the way up the tree. And I have to remove a whole bunch of things before I merge. All right, but that's it for 2-4 trees. Any questions? Again, no code. I just want you to be aware of the general structure so that we can, I mean, you have to know this for the final. I will tell you there will be at least one question on 2-4 trees on the final exam, but it's also very useful in terms of understanding red-black trees. But any questions on that? Okay. In fact, red-black trees they're a beautiful data structure. They work really well, but they are opaque. Like, it's very hard to understand. I will show you the textbook. So in the textbook, I have a bunch of, can I draw on this? Probably not, whatever. Here are a bunch of operations, but that's not it, right? We have to do something like this. The thing about the red-black trees is it's a lot of cases, and at some point, it's real easy to lose track of why we're doing something. It's very hard to understand. It's very hard to grok it, let's say, to use a word from the quote. They're very hard to understand, except if you, and it says here, the following discussion is probably impossible to follow without referring to this figure or recreating it on a piece of paper. Indeed, the reader may wish to study this figure before continuing. It's very hard to understand on its own. So we're gonna take the easy way out, and we're gonna map them to red-black to 2-4 trees, right? Because they are sort of, a red-black tree is a 2-4 tree implementation. But on a binary tree. Sam Altman, right? So famous in AI, CEO of OpenAI, and ChatGPT, the sort of CEO of the company that created ChatGPT. Great execution is at least 10 times more important and 100 times harder than a good idea, right? I like this quote because a lot of people put a premium on ideas. I've had people try to get me to sign a non-disclosure agreement before they tell me their idea. And I got to tell you, I agree with this 100%, and maybe these multipliers are not even as high as they should be, right? Execution counts way more than an idea. Although there is something to be said for being first to market with an idea. Like Uber sort of always has a bigger platform than Lyft. They would have to do something to screw it up in order. But great execution, way more important than a good idea. Anyway, so red-black trees. So you can see here, this is a binary search tree. Has a binary search tree property, and each node has 2 children. Some of these nodes are colored red. And so yeah, a red-black tree is a binary search tree that has a logarithmic height. But instead of rebuilding like we do with a scapegoat tree, we rotate, sort of how we do with a tree, right? A red-black tree on n values has a height at most 2 times the log of n. Add and remove run in big O of log n in the worst case, and the number of rotations during add or remove is constant amortized. So if you do the red-black tree from the textbook, then the rotations add and remove is constant amortized. We're not going to do that because, again, it's very hard to understand. If you want a red-black tree implementation, you can go to Wikipedia or any number of resources and find a correct one. We're going to try to understand it rather than implement it. Implementing it is just a question of copy and paste, right? So in our, we're going to look at add and remove. We're going to map it right to the 2-4 tree. So I think it is actually still constant amortized, but I don't have a proof for that. Very widely used data structure, right? So The Java collections framework, again, I suspect that tree set is a red-black tree, but you know, they are mum on things like that, so they can change them. The C++ standard template library, same deal. They probably wouldn't say, but most likely that's what they use. The Linux kernel is definitely used in there, or at least it was for many, many years. And a red-black tree is actually, there's not just one implementation of a red-black tree, it's a family of implementations. They maintain certain invariants that guarantee good performance. They do have a lot of things in common, but how you implement them, there are some choices you can make. So we're going to define our own. Just basically map all our operations directly to the 2-4 tree. And again, like with the 2-4 tree, we're not going to dive into the code. I don't think there's anything to be learned there. If you ever want to implement one, copy and paste, I would recommend. Right? Looking at an implementation almost certainly will not help us to understand it. All right. So to start with, it is a binary search tree, but we're going to add, right, a binary search tree is a node with a parent and 2 children and a piece of data, and we're going to add a color to it. And this color can be red or black. Pat chose byte. I'm not sure if Boolean would have been more memory efficient, or maybe it doesn't matter, but so 0 for red, 1 for black. And in our diagrams, it was just easier for me to draw if they're colored white. It was just less work. So the black nodes will actually be white, and the red nodes will be this nice pink. And yeah. So red-black trees have 2 main properties that we're going to maintain. The black height, right? So here I've put, unlike with the 2-4 trees, I did not put the nil nodes, but here they are kind of important. So the nil nodes are here. A lot of the diagrams, they won't be there, but of course, just understand that every leaf in the 2-4 tree is a nil node. And so black height, there are the same number of black nodes on every root to leaf path, right? So I start from here, that's 1, and then I can go 2, 3, 4 to get to this leaf. Or if I go this direction, it's 2, 3, 4, or 3, 4. So if I'm just counting black nodes on any path from the root to the leaf, it's always the same in this tree. Sorry, questions? And this requires us to include nil nodes because, for instance, you know, if I had, it's hard to show it here, but I could have, for instance, well, I don't know. This is not a good one. This is not a good example. But the nil nodes, there are instances where if I didn't have a nil node, it's sort of ambiguous. So we put the nil nodes in. So and they count as a black node on the path. And no red edge. So a red node cannot be the parent of another red node, right? And you'll notice that I do not have any 2 red nodes connected by an edge in this tree. So no red edge. If there was a red edge, then it would be, I would have a red node here, and the parent would also be red. So red nodes cannot be adjacent, no red edge, no red parent for a red node. Those are all equivalent statements. Okay, so a red node must have a black parent and 2 black children. If we're including nil nodes, that would include even the root, but the root is never going to be red in our implementation. It could be, but we're not going to do that. So yeah, observe we can always color the root black without violating these properties, right? So this could be red in certain instances, right? In this one, and then I still have all the same properties, but I can color it black and I still have all the same properties. So we're always going to keep the root black. All right. Right, to show that they're isomorphic to 2,4 trees, well, let's take a look. See, our claim is that structurally they're the same. So each red node, of course, has a black parent. So we think of our black parent as the sort of center of our 2,4 tree node. Okay, so I'm going to gather, so this red node here has a black parent, and so I'm going to consider this one node in my 2,4 tree. And these two red nodes have a black parent, and this will also be considered one node in my 2,4 tree with 3 pieces of data, right? So this one has 2 pieces of data and 1, 2, 3 children. And this one has 3 pieces of data and 1, 2, 3, 4 children. And this child has 2 pieces of data in it. So I can basically restructure my red-black tree. I just redraw it. And then I could put, some fancy squares around it if you want. And there's my 2,4 tree. Okay. And even the operations, right, to jump from here to here is one move in my 2,4 tree. It's also one move in my red-black tree. Okay. Questions? Right. So that's what isomorphic means. It means basically they have the same structure, but implemented slightly differently. The nice thing about that is we can use the things we know about 2,4 trees to prove things on our red-black trees. But yeah, so if a 2,4 tree node has a single piece of data, the data is black, right? As in here, if we add additional data, then it's red, right? So there's a red one here and here and here. Yeah, and to keep it simple, right, we could structure this a little bit differently, but we'll always keep black in the middle. Okay. So we're going to show an important property of red-black trees, that the height is logarithmic in the number of nodes. You could make that argument from the similarity to 2,4 trees. We'll just do it fresh. Every black level, right? So when I draw my 2,4 trees, you might notice that I'm keeping the red nodes on their own level and the black nodes on a separate level, right? Because every black path has the same number of black nodes. So if I just sort of ignore the red nodes and pretend they don't exist, then I have a perfectly balanced binary tree. Well, not really, but it's not really a binary tree. There's 3 children here, but you get the idea. Basically, I have like a 2,4 tree, right? And yeah, and it's easier to see that I have the same number of black nodes on every root to leaf path. So how many black nodes are there on every root to leaf path? Well, there are n plus 1 nil nodes as leaves. We'll leave that for you to convince yourself that that's true. But that implies that every root to leaf path encounters at most log of n plus 1 black nodes, right? If I have n plus 1 leaves, and I had to basically at least double the number of nodes I see in each black level, then to get here, I get there in log of n plus 1 steps. It's sort of it's a bit hand wavy, but it's the same idea that we've seen a few times already. Right, questions? Also, at most every second node along the path is red, right? Maybe I encounter a few red nodes. I do not counter more than 1 red node in a row. So it's at most every second, and it cannot be the leaf. So that means I have at most log of n plus 1 minus 1 red nodes, right? It has to be at least 1 less than the black nodes because my root and my leaf are both black. So that means any root to leaf path has log n plus 1 black nodes, log n plus 1 minus 1 red nodes. And you can do a little bit of math and convince yourself that it's at most 2 log n. So the height of my red-black tree is at most 2 log n, And that means that all of my operations, my find operations, run in 2 log n time. All right, questions? Okay. So every search path is at most 2 times the log n steps. And so yeah, we have the basic structure down. We've shown that it's logarithmic height. Find should work very, very well. Now we want to add and remove to this tree while maintaining these red-black tree properties. And how we're going to do it is we're going to just look at the 2-4 tree, the operations that we just saw, and we're going to replicate them in a red-black tree. Right, so that means we want to be able to split, we want to be able to merge, we want to be able to borrow. So to start with, we're just going to do a little warm-up, light warm-up, look at a couple simple cases, and then we will look at the examples we just saw in the 2-4 tree. That might take us to the end of class, we'll see. Okay. So here's a red-black tree. I'm going to add, I've kind of drawn in, these are my 2-4 tree nodes. I'm going to add a new node. When I add to a red-black tree, do the same thing as a regular add in a binary search tree. I follow the search path. I color the node red and I add it, at the end of my search path. Okay, so I have an example here. Yeah, so we call add 3.5. My search path, well, it's less than 6, it's less than 4, it's greater than 2, it's greater than 3. I've run off the end of a tree, so I make a new node with 3.5 in it, and I color it red. Okay, so I'm not violating the number of black nodes along any root to leaf path, but I am violating the no red edge rule, right? So I cannot have 2 red nodes next to each other. So I have to fix this. Okay. Yes. Every time I add, the default color is red, and then we're going to fix it. The textbook has detailed instructions, but at some point, every red-black tree implementation devolves from something that you can understand to just trust me, it works. Here's a very complicated algorithm. So what we're doing is not necessarily the most efficient thing, but hopefully it'll be easier to understand. Okay, so what does this mean in terms of our red-black tree, or sorry, our 2-4 tree? Well, in our 2-4 tree node, that means we have a node with 4 pieces of data, right, which we're not allowed. 1, 2, 3, 4. And when that happens, we split the node. We send the middle element up to the parent. So how do we split in a 2-4 tree, or sorry, a red-black tree? Well, it turns out that's not difficult at all, right? And in fact, I'm just going to push black down from my parent into my 2 children, right? So 2, I've added this. I have a red edge here. The grandparent of the node that I added is 2. It's black. It has to be black, right? Because there cannot be a red edge. So I'm going to do what's called a push black operation. So I'm going to move black from 2 down to the children. What that means is that, well, the number of black nodes on any root to leaf path is still the same, right? Because I encounter either 1 black node here, or I encounter 1 black node here, or if I made a right, I encounter it down there. So same number of same number of black nodes on each root to leaf path. I've eliminated this red edge. And in terms of my 2-4 tree, I've moved 2 into the parent. But all I did was change the color, right? And then so now this is a node. The 2 and the 4 together are a node. The 1 alone is a node. The 3 and the 3.5 are a node in my 2-4 tree. Okay, so make sense? Questions? Sometimes it's simpler. Other times it's way worse. Of course, we can do a merge operation to reverse this. I don't think you do exactly the reverse of this, though. At least not in our implementation. But you can do something similar to the merge operation. You can pull black to the parent, right? And again, you're going to keep the same number of black nodes on every root to leaf path. Okay, so that's the add. If I borrow something, it requires rotations with changing color. We'll get to that. Yeah, so if I want to, so that's one operation, right? A split. If I want to borrow, that involves a rotate right and a push black, rotate right, depending on, oh, this is brutal. I think I am missing something important here. Sorry. Beat it. I'm just going to temporarily move over here because part of my red-black tree is being blocked. Though to be honest, this is, I mean, I complain about Microsoft, but OneNote is pretty good. Oh, wrong one. Okay. So let's say we make a call to remove 14. And this is in terms of my 2-4 tree nodes, this is one, this is another, and this is me all by my lonesome. And I'm deleting 14, and now I want to borrow from my sibling because my sibling has a extra node here. So we're going to do a rotate right and a push black. And so if we do operations, I'm going to remove 14. I'm going to rotate right at my parent, which is 13, to bring 12 up. And then I'm going to push black down. But in terms of a red-black tree, I don't have to do that, right? So if I want to keep mimicking my 2-4 tree, then I'm going to push black down from 12 into my nodes. And I've effectively borrowed from my parent, right? I still have a parent node with the same number of data, but whereas my left child had 2 pieces of data, now it has only 1, and I will have 1. So that's to imitate my 2. But once I've reached this point here, actually, I don't need to do, right? In terms of my red-black tree properties, I could stop right there. So although we are mimicking the 2-4 tree, if we were serious about a red-black tree implementation, we could stop here. We could make some of our cases a little bit easier. But we're not going to do that because, again, if you want an implementation, you can find one in many different places. We want to try to build an understanding of how by tying these two implementations together, the 2-4 tree is a little bit easier to understand. We can prove things about the red-black tree. Questions? Okay. Yeah, so we could have stopped before the push black operation. At this point, the red-black properties were restored. And yeah, so we're doing a one-to-one mapping, but most people don't do that if they're serious about a red-black tree implementation. Okay. Yes. And yeah, for a job application, I was interviewing at some university on the East Coast, and so you have to do a teaching presentation and a research presentation, and my teaching presentation was 2,4 trees, and I did sort of an introductory, and sorry, my teaching presentation was red-black trees. I did sort of the introductory 2,4 tree thing, but I did very preliminary. I kind of followed Pat's book very closely, and when I got to the red-black tree, I taught the red-black tree from like first principles. We're just maintaining red-black tree properties, and here's how we do it. And at the end of the presentation, I turned around and I just see like confusion in all of the other professors' faces. So I don't think there's anything to be learned by just grinding out the cases in a red-black tree. Especially, I didn't get the job, obviously, but I'm sort of happy about it because I didn't really want to move to the East Coast. But yeah, anyway, sort of a related story. Okay, so we're going to go through a couple of examples, same examples that we saw before. We're going to implement a particular type of red-black tree called the leading red-black tree. Let's see if I can. I can't get rid of that, huh? I could do this. Yeah, I could do that. All right, I'm going to teach from here because I suspect that there might be other slides that are blocked. So we'll stick with OneNote. So we're going to do a left-leaning red-black tree, which means that because there are different implementations that could correspond to 2,4 trees, but we're going to make sure that we have sort of this one-to-one correspondence. Right, so red-black, left-leaning red-black tree means if I have one red child, it's the left child. Right, so I'm always going to maintain that, even though it's a bit of a pain, but yeah, it makes sort of the number of cases we have to look at a lot less. We're not going to look at every case, and we're not going to develop the rigorous algorithm. You can read the textbook for that if you want. We just want to practice a little bit. Okay. So add 3.5, my left-leaning red-black tree. I'm going to search for 3.5. Obviously, it's going to be added. Yeah. But before we do that, let's look at our 2,4 tree. And I'm going to color in the data elements so that we can see the equivalent 2,4 tree to our red-black tree. Okay. So when we add 3.5 to our 2,4 tree, what happens? Well, now I have a node, right? I follow the search path. The search path takes me here, and 3.5 goes after 3. But now I have a node with too many data items, so I'm going to split it. And I'm going to split at 2. 2 will get sent up to the parent, and now I have, the root has 3 data items, and I have 4 children. I'm going to recolor these, right? So, yeah. So I have my left-leaning red-black tree, right? So if I have the red piece of data is always on the left if there's only one, or the red child is always the left child if I'm in the 2,4 tree. Okay, so that's the operation on the 2,4 tree. We're going to mimic that on the red-black tree. Right? Questions? Okay, so we add 3.5, same as we did before. We have to do the split operation. So we're going to move 2 to the parent, which means that we're going to push black down to the children. One little piece of house cleaning. I have sort of the 2,4 tree or the 2,4 tree node here, but red is on the right. I'm going to rotate it to be on the left. Bit of a pain, but does reduce the number of cases we have to look at. So I'm going to rotate left at 3, and that will put my black child or the red child to the left of the black parent. So I've split that, but now I actually have a red edge. But this is still a node with 3 data items, right? So this is still a legal node. I don't really have to split it, but I'm not violating any 2,4 tree properties, but I am violating this red-black tree property. So I want it to look like this, which means I want 4 to be the root and 2 and 6 to be the children. So I'm going to do a rotate right at 6, but also a recoloring as I do that. So to rotate right, right, yeah. Let's, so 4 goes to the top, 2 is still the child. The right child of 4 is 5. Well, the right child of 4 now becomes 6, and 5 becomes the left child of 6. And 10 is still the right child of 6, right? So that's a standard rotation. This right child of 4 becomes the left child of 6, and 6 becomes the right child of 4. And we just flip the colors as we do that. So 6 goes from black to red, and 4 goes from red to black. And then lo and behold, we have our red-black tree that corresponds to our 2,4 tree. Okay, so now there's a lot of different ways we could have done that. Again, we're just sticking close to the 2,4 tree. Questions? Okay, let's do a slightly more complicated one. Same thing, but now my root is full, right? So if I look at my 2,4 tree implementation, I'm going to split, when I add 3.5, I'm going to split the 2. The 2 is going to go here, and I'm going to have to split the root again. Right, so I add 3.5. I send 2 up to the parent because I have too many data items, but now I have to split my parent as well. So 6 is going to become the new root of the tree. And I have to recolor 4, and I'm going to recolor 8 as well. So I'm starting here. I'm going to add 3.5. I want to end up in black tree equivalent of this. So add 3.5. I push black down to the children. I do a rotation here to keep this left leaning. Now, whereas before we did the rotation at 6 in order to move 4 up to the root, now I have to do a split. A split is a push black operation. So I'm going to do a push black. These 2 guys become black. The root becomes red. And then I just recolor the root black because I always want the root to be black. So that's slightly easier. Actually, splitting in a 2,4 red-black tree is easier than the 2,4 tree. Yeah, question? Okay. All right, we'll look at a couple more. We'll look at some removes, and then maybe we'll go through them a little bit quicker. There's no point in belaboring this, but let's say I want to remove a 5 from this red-black tree. And this is my 2,4 tree. 5 is the root, so I have to find the in-order successor on my red-black tree. That means I step to the right, and then I go left as far as I possibly can. So 6 would be the in-order successor. On my 2,4 tree, I do the same thing. I go down to the left. I take a step, then I go down to the left until I hit the leaf, and then I take the leftmost value. So 6 is the in-order successor there. So 6 replaces 5. This gets deleted, and that's it. With the red-black tree, same thing. 6 replaces 5, and then I can delete this. So yeah, that's an easy case. So I wanted to remove 13 now, right? This is, I want to borrow from my sibling, but the sibling doesn't have anything, so I'm going to borrow from my parent, and I'm going to merge, right? So I removed 13, I moved 12 down, and I merged it with the sibling, and that's it. I'm good. This did not leave my parent empty, so I do not have to merge again. The equivalent operation on a red-black tree, I remove 13. Right now, I want to get to this tree from here. So, well, this is, I mean, I want the 12 to be black, and I want the 11 to be red. I want if I have a red child, it's going to be left. So I only have one red child. So I'm going to, basically, the first step I'm going to do is, I'm going to move this black up to 12. This is going to, right? I removed a black node here, which means that the root to leaf path has one less black node. I have to correct that right away. So one way to correct it is to borrow the black from the sibling. But at this point, I'm basically done in terms of my red-black tree, if I want it to be. Right? My red-black tree, all of the properties are restored just with that one move. Yeah. Again, if we're doing an actual implementation, we're not going to grind out everything. We're not going to make it exactly the same as the 2-4 tree. But just for the fun of it, let's get to this. So we want to, oh, is that right? No, that's exactly right. Sorry. Oh yeah, that's all we had to do. Sorry, different example. Yeah, so that operation to borrow from my sibling was just to push a color down. That's it. Okay. Here I'm going to remove 9, and this is going to be a borrow operation, which is going to be a bit of a pain. So in the 2-4 tree, I borrow from my parent, and the parent borrows from the sibling, and I end up in this situation. So let's try and mimic that in our red-black tree. I remove 9. I want it to look like this. So I want 11 to be up here somewhere. But, sorry, this was the one. Instead of moving 11, yeah. So if I'm following the red-black tree implementation, I want 11 to be the parent of 12 and of 10, and that's going to require a bunch of rotations and recoloring. But if I'm simply looking at the red-black tree, then to fix this problem, I'm just going to move the black up from 7 to 8, and that's it. I'm done. I don't have to do anything else. The red-black properties are restored. It doesn't look like this, of course, right? It looks like a different 2-4 tree. But yeah, so in terms of practical implementation, they do diverge. But if I did want to follow this up and make it look exactly the same, I could, I remove the 9. I want to get 11 up to this position, so I rotate right at 12, and then I rotate left at 10. And then 11 is the parent of 10 and 12, and I've made it black. And then I'm going to rotate right at 10, and then I have basically the same tree. Again, that's a lot of work to get to a place where, you know, we were in one move earlier, but again, the whole idea is to sort of understand why we do these things. And if you're stuck, you can always fall back on the 2-4 tree implementation. All right, questions? Okay. The last thing we'll do before we finish our red-black tree. Again, this is just to get a feel for things, but so this merge all the way up the tree, we've seen how to do a split. Basically, it's just a push black, very easy. To do this borrow and merge operation, well, let's say I'm removing 12, right? So 12 is here. I remove it, I borrow from my parent, I move in with my sibling. Now my parent is empty, so they borrow from their parent. And then they move in with their sibling, and now the grandparent is empty, so they borrow from their parent, and they move in with their sibling. That was that sort of cascading merge in our 2-4 tree. To see the equivalent in our red-black tree, well, I'm going to remove 12, which is here. And then I'm going to, from here, I want to end up in this tree. So, well, I can kind of cheat and say, well, I know the 13 has to be a left child of 15 and it has to be red. So I'm going to do a left rotation here, and I'm going to color 13 red. And then I can see that, well, 8 and 11, 8 should be colored red. So I can do that. This is a little bit trickier, and I'm going to kind of go back to what Pat does in the sense that, well, one way to make sure in a red-black tree that you're doing the correct operation is to, when I remove a black node, is that I do a double black parent, right? So I remove 12. I've ruined this root to leaf number of black nodes, so I'm going to paint this double black. But that means that I'm going to paint this red. And then to maintain the left-leaning property, I'm going to rotate it. Now this is double black, and the child is red. And what I'm going to do is I have this extra black. It keeps that root to leaf black node property. But at some point I have to ditch this second black, right? So what I'm doing is I'm going up the tree and I'm trying to find a red node that I can dump off this black, extra black to, right? So that's another way to think of it in terms of purely the red-black tree. So I move the double black to the parent, and then I have to color the left child red, because in order to keep the root to leaf black property, and then I am going to rotate left at 16, and yeah. When I rotate left at 16, 16 turns red. Yeah, and then I've restored. So I've given my well, the anyway. Still, even all these years later, I'm still having trouble with this red-black stuff. The idea, though, is that if 16 turns red, then I've changed. I'm maintaining the number of black nodes on every root to leaf path, right? Again, I'm not going to belabor the point too much. I think we've spent enough time on technical details. I just wanted you to have sort of the beginnings of an understanding of the red-black tree and why we make the choices that we do. And hopefully mapping them to the 2-4 tree makes them a little bit easier. But yeah, we'll stop there. Questions on that? All right. So red-black tree implements the sorted set interface. The red-black tree supports the operations find, add, and remove in O log n time per operation. That is something we borrow from the 2-4 tree proof, right? Since we can map all of the red-black tree operations to the 2-4 tree in a sort of a 1-to-1 correspondence, all of the things that we proved about the 2-4 tree are also true of the red-black tree, which means the amount of rotations are amortized. They're log n, each move operation does at most log n rotations and recoloring. But if you wanted to do a deeper analysis, you can prove that they're constant. But yeah, so we'll stop there. Questions, red-black trees? Okay, let's see it in action. So again, we're going to add a ODS red-black tree to our sorted set tests. So now we have a skip list, we have a treep, we have a scapegoat tree, we have the Java red-black tree, and then we have the ODS red-black tree. So we're going to, yeah, that should be fun. So random insertions, our ODS red-black tree is the best. It beats the tree set, which is probably also a red-black tree, and it beats the scapegoat tree. The contains, the ODS red-black tree again is the best, right? It's complicated, but it's effective. It runs very, very, very well. And, you know, again, there's so many correct implementations out there. Removals, it's still the fastest. Headset, fastest again, except for the skip list. It's still, splitting a skip list is still easier than splitting any kind of tree. Iteration, it is the fastest. Versions, not quite as. No, that's interesting. Headset, very fast, not as fast as a scapegoat tree. That is probably, yeah. I'm guessing that's an artifact of whatever random implementation it happened to be doing that time, but yeah. So the red-black tree, the ODS red-black tree is, for the most part, the fastest sorted set we've seen so far. All right. Okay, so we're going to start on binary heaps. So we're going to step away from the, well, it's still in some sense a binary tree, but we're going to step away from the sorted set interface, and we're going to look at priority queues. Right, so heaps are, they're kind of cool. The quote of the day, the first step in any project is to grossly underestimate its complexity and difficulty. I think every student and former student can relate to that. But yeah, any project in general. So heap is sort of an implicit binary tree, which means we're not really going to implement it as a tree. We're going to implement it as an array. But it is a very popular implementation of the priority queue interface. It's very good at just keeping things the lowest priority element ready to be removed. So a heap is a disorganized pile, but in this case, our heap means it's semi-organized, right? So binary search tree would be a fully organized, right? Everything is in, I can do an in-order traversal and get back everything in sorted order. Heaps, you can't quite do that. If I do an in-order traversal, I'm not going to get sorted order. I'm going to get some kind of almost starting to look like sorted order. For us, it means it's organized enough. So look at two types of heaps. The one is an implicit binary tree called a binary heap. The other is an actual binary tree called a meldable heap. Both are pretty cool. But yeah, I think the binary heap is the more popular one for a few reasons. One, because if you can do it in an array, that's great. That's a compact piece of data, which always runs well. But the other thing is that you can do heap sorts from it, which is an in-place sort. So we'll see that as well. The second version uses an actual binary tree, but basically has one operation. It merges two binary trees, two heaps into one, and we can see that we can do add and remove just doing that. And that's called a meldable heap. Okay, so this implicit binary tree implementation based on, and now I don't know if I'm pronouncing this correctly, but sure, I'll try that. He developed a method for tracing a family tree. And the problem he was trying to solve is that he was writing down family trees in a book for a person, but he wanted to very quickly be able to find some distant relative, right? So we know exactly what page your grandparent was on, or your great-great-grandmother, or your great-great-great whatever, right? So all of these he wanted to find quickly. So he wanted to be able to calculate quickly what page an ancestor was on. You can sort of see how that might relate to a binary tree, but in this case, the binary tree looks upside down. Right, so this is your family tree. This is you. This is mom, dad. And then your mother has grandmother and grandfather on her side, and your dad has a grandmother and a grandfather on their side. And you can keep going up this family tree. And what Eitzinger wanted to do is take this family tree and put it in a book. And you can think of a book as an array, right? So each page is just a piece of data that I want to look at. So yeah, you're at the bottom, your left and right parent, or mother and father. Next level up is your grandparents, etc. Okay. And then you could sort of number these as pages. So this was you, this is page 0. And then your mother would be on page 1. And your father would be on page 2. And then the maternal grandmother was on page 3. And the maternal grandfather was on page 4, etc. Right? So we're just going to number the pages starting at 0, and then 1 and 2 and 3 and 4. And what Eitzinger saw was that mathematically, it's easy to compute a jump from, say, mother to grandmother or grandfather, right? Even though this is a jump of 3 pages, Eitzinger saw that you could just mathematically compute it. Okay, so we're going to take the same idea. Instead of a book, we're going to store the data in an array. And it's going to be an implicit binary tree. So this is, we want to do operations on this thing, but we want to instead do equivalent operations on an array. And to do that, we have to be able to, for instance, if I give you the index of a node, right? So this node here is located, or whatever data or thing of interest I have is located in this memory location in my array. And if I wanted to, for instance, figure out where in my array are my 2 children, how could I do that? So I'm going from index 5 to, for the left child, index 11, and for the right child, index 12, right? And that should work everywhere. So if I'm at page 4 or location 4, I want to find my left child, I want to go to index 9. And my right child, I want to go to index 10, but I want to be able to I'm going to give you 4, and you're going to compute the index of the left child and right child. And for 3, it should work for everyone, right? So yeah, what's the pattern? Or does anybody spot? Or is it we're 2.5 hours into a 3-hour class and everybody's... So there's a pattern. It's a simple pattern, right? So if we just get, and maybe we could start from here. Well, from 0, it's 1 and 2, but from 1, it's 3 and 4. So they're always, my 2 children are sequential, right? So if I go from 3 to my left child, then I add 1, I get to my right child. So whatever I compute for my left child, the right child is left child plus 1 in some sense. But as it turns out, I could just double my own index and add 1 for my left child. And then double my own index and add 2 for the right child, right? So 2 times 0 plus 1 equals 1. That's the left child. And 2 times 0 plus 2 equals 2. That's the right child. And 2 times 4 plus 1 equals 9. That's my left child. And plus 2 equals 10. That's my right child. Okay, so I can child, right child in an array. So I can, in some sense, traverse my tree just by doing these calculations. Okay, questions? Okay. What about if I want to compute the parent? So that's a little bit trickier because I have, well, if I want to compute the parent, am I a left child or a right child? Like, that's going to matter, right? If I start with my child, or I start with myself, so let's say I'm here, I want to compute my parent, but I know how my parent computed my location is they took their location and 2i plus 1 gave them my location. So now I know my location, I know k, and I want to solve for I. Right? This is basic algebra. So k is equal to 2i plus 1, where k is, k is my location, and I want to figure out my parent's location. 2i equals k minus 1, so I is equal to k minus 1 over 2. So a little bit of algebra. If I'm given 3, and then I say, well, my parent is at I equals 3 minus 1 over 2. That's 2 over 2, which is 1, which is correct in this case. Okay, so just a little bit of algebra working backwards from how I got to the children. I can get back to the parent. Questions? All right. What do we notice about the left child? Anything? Or anything? I mean, anything at all, I guess, but. If I look at the index of left children, what is something they all have in common? Yeah. Sorry? They're all odd, yeah. So, which is nice. I mean, it means this is always going to give me an integer. But yeah. So left child of the root is 1, it's odd. Left child of 1 is 3, it's odd, right? This is in some sense the definition of an odd number, 2i plus 1. Okay. Right child, again, I have a formula for the right child. I'm just going to solve for I given k. So k is, if I have I can determine k, but I want to do the opposite. I have k, I want to determine I. So after a little algebra, of course, not surprisingly, I get k minus 2 over 2. And of course, the right child is always going to be even. So if I'm at 4 and I want to determine my parent, well, that is I equals 4 minus 2 over 2 equals 2 over 2 equals 1. And since it is even and we subtract 2, the answer is always going to be even. Divided by 2, we'll always get back an integer there as well. Okay. But when we go to implement it, we can kind of take advantage of Java. We can do integer division, right? These are only different by, right? If I want to determine the parent of, let's say, 9 and 10, my argument is that I can use this formula in both cases. And because this is integer division, it's going to give me back the correct number, right? So if I'm the right child, or let's say, sorry. So I have that right? Hopefully I have that right. If I'm the right child, and I want to find my parent, well, my value is 9. So I want to take 9 minus 1 over 2 equals 8 over 2 is 4. And that indeed brings me to 4. But let's say I am at the right child, so I'm at index 10. Then I have 10 minus 1 over 2 equals 9 over 2. But because this is going to get cast to an int, I can't remember if this is integer division in Java. If it's not, it will be converted from a float to an int when I return it. In either case, this 4.5 will become a 4. So this formula will work for both left child and right child. Okay, so that means using these functions and an array, I can simulate a traversal through my binary tree. If, from here I can get to, any child that I want. I could do if I wanted to, I could do a binary search through my array, which is now acting as an implicit binary tree. Questions? Okay. All right. So the thing about this implementation is that if I did not have a full binary tree, right? So this is a nice looking binary tree because, well, basically every level has the maximum number of nodes except for the last level. And the last level is filled up from left to right, which means that if I look at my array, all the data in memory is contiguous. It's all side by side. So if I'm implementing a regular binary tree that can have sort of weird shapes, then I might have an array that's full of null data, right? Full of holes. That's going to be wasteful. So our binary heap, though, has this nice property in that all my binary trees that represent my binary heap are going to be as complete as possible. So all the data in my array will be contiguous, and all of my binary heaps will look something like this. It'll be a nice looking tree, maybe a few leaves missing from the end. Okay. So now if I want to add data to my implicit binary heap, well, all I'm going to do is, for instance, I want to add something in the next location. Well, the next location is 12, and I put some data there, and it's simply going to be, I just push it on the back of my array. Okay, so yeah. If I add something, it's added as a leaf in the last location, which corresponds to the last location in my array. And yeah, that sort of works out nicely. So now to make a heap, what we're going to maintain is, and we saw this with treeps, where our treeps maintain the binary search tree property, but also the heap property, which means that, well, for the heap property and the treep, we used a priority, but now the priority is going to be the data, right? This is a priority queue. So the heap property is that yeah, sorry. my parent is going to have a lower priority than me, right? So if I look, starting here, I look at the parent, the data is 80, it is less than 87, so this is, maintains the heap property. If I look at the parent of 80, it's 8, 8 is less than 80, so this still maintains the heap property. And this is true of every parent-child relationship in the tree, right? So now, I don't necessarily have only things that are less than 3 in the left tree and only things that are greater than 3 in the right tree. That's binary search tree. So here you can see everything in the left tree is actually less than 3. Yeah, just the heap property. Okay. 5 minutes. Okay, well, let's look at add. We can repeat this next week if we have to, but let's say I want to add things to my heap. Well, the nice thing about my heap is that location 0 is, if I maintain the heap property, always has the least thing in my priority queue, right? So that's how I maintain the priority. That's how I can return the minimum element in my heap in constant time. If I remove it, then I have to do a little bit of restructuring, but it's not too bad. But yeah, that's how this heap property maintains the priorities of this priority queue. But now I'm going to add a new piece of data. As mentioned, it goes into the last open element of my array, which corresponds to the next open leaf position in my binary heap. And you can see I've added 5, and now I've violated this heap property because 5 is less than 31. So I kind of want to move 5 up my heap until I fix this heap property. Okay. And how I do that? We will see in a second. Well, I'll just go over it in very high level. I mean, it should be sort of clear. I'm comparing myself or this node to the parent, and I'm saying, oh, do I violate the heap property? And if it does, I'm going to swap, right? And then once 5 moves up here and 31 is here, I'm going to again compare 5 to my parent, and if it violates the heap property, I'm going to swap them. So 12 goes down here and 5 goes up there. And then I compare it to my parent, and in this case, the heap property is maintained. 3 is less than 5. So basically, I take this 5 that I've added here, and I bubble it up my tree, which corresponds to it jumping, what does it jump to, 12? And then it jumps up, or sorry, it jumps to, I have a couple 12s in here, jumps to 31, and then it jumps to 12. So yeah, that's basically it. We do a bubble up, and we'll see next week that we can do a remove. It's sort of an opposite, a trickle down, and then yeah. So we'll pick up next week with this, and then next week we will also, when we finish up this, we'll look at graphs, which will prepare you for your assignment 5. But in the meantime, make sure you get your assignment 4 in, and yeah, so the August long weekend is still going to be class canceled. I don't think we won't need that extra class, but there will still be office hours that week, just not on the Monday, right? Every other day. Okay, so that's it for today. I can answer any questions you guys have, but other than that, I will see you next week.